Section: Introduction. In this section, we explore whether modern AI agents can make strategic decisions in uncertain situations. We focus on the Iterated Prisoner's Dilemma, IPD, a classic game theory scenario where the best individual choice, defecting, leads to worse outcomes for both players. When the game is played multiple times, factors like reputation and retaliation become crucial, as defecting can lead to punishment in future rounds. Axelrod's early computer tournaments demonstrated that a simple strategy called tit for tat could outperform more complex strategies, leading to significant research in evolutionary game theory and cooperation. We note that previous experiments have expanded on Axelrod's work by introducing various factors like noise, different population structures, and advanced learning algorithms. However, two main issues remain. The agents are either manually programmed or use basic algorithms, and their reasoning processes are often unclear or non-existent. With the advent of large language models, LLMs, we now have a new type of reasoning agent that could change decision-making in uncertain environments. The emerging field of machine psychology aims to investigate how these models exhibit human-like decision-making traits. We take this opportunity to revisit the IPD using LLM agents to see how well they can reason in natural language, adapt on the fly, and reflect on their decisions. These LLM agents can process prompts, generate justifications for their moves, and potentially adjust their strategies based on reflection, making our experimental setup more akin to human behavioral studies while still allowing for controlled simulations. Our contribution includes the first evolutionary IPD tournament featuring both classic strategies and contemporary LLM agents from OpenAI, Google, and Anthropic. We conduct a series of experiments that vary model capabilities and termination probabilities, along with additional tournaments designed to test the limits of advanced models. We aim to benchmark LLM strategies against traditional baselines, explore how these models approach the tournaments, and examine the effects of game horizon and adversary modeling on their success. We find that LLMs perform well across various conditions, with advanced models generally outperforming basic ones. We also discover that these models do not simply memorize strategies. They exhibit unique strategic styles and adapt to their opponents. Furthermore, we observe that the models consider the length of the game and the behavior of their adversaries when making decisions, indicating a deeper level of reasoning. Our findings suggest that LLMs are competitive in all tournament variations, rarely being eliminated by selection criteria. They display different strategic fingerprints, with OpenAI's models being more cooperative compared to the adaptable Gemini model. Overall, our research contributes to the understanding of AI decision-making and the ongoing debate about the reasoning capabilities of LLMs. Section Summary. In this section, we investigate the strategic decision-making capabilities of modern AI agents in the context of the Iterated Prisoner's Dilemma, IPD, utilizing large language models, LLMs, to explore their reasoning and adaptability. Our findings reveal that LLMs are competitive across various tournament conditions, demonstrating distinct strategic styles and the ability to reason about time horizons and adversary behaviors, thus contributing to the ongoing debate about their cognitive capabilities. Section: Method. In this section, we describe our experimental design, which involved a series of evolutionary tournaments. Each tournament had 5 phases where a group of agents participated in round-robin Iterated Prisoner's Dilemma, IPD, matches. After each phase, agents reproduced based on their average scores, forming a new population for the next phase. Our main experiment followed a 2x2 factorial design, focusing on model capability and termination probability. Each combination was tested once, resulting in 276 matches per phase with a fixed group of 24 agents, and we conducted 5 phases in each tournament. The best-performing agents were more likely to reproduce, allowing us to study the evolution of cooperation and reputation. In the final tournament, we included 3 large language models, LLMs, and introduced a competitive model from Anthropic. For the match procedure, we used a classic payoff matrix where the reward is 3, the sucker's payoff is 0, the temptation is 5, and the punishment is 1. At the start, each agent had no history and a set termination probability. In later moves, agents could see the history of previous moves, up to 20 moves. Each match could end after each pair of moves with a certain probability or after a maximum of 30 rounds. The likelihood of reaching this maximum varied with the termination probability, being about 4.7% at 0.1, around 0.024% at 0.25, and less than 10 to the power of -16 at 0.75. Each phase included a specific number of matches based on the number of agents, leading to the 276 matches we mentioned. We implemented 10 classic IPD strategies, coded in Python, based on previous research. These strategies included 1. Tit for tat, TFT, starts by cooperating and then mimics the opponent's last move. 2. Grim trigger, GT, begins with cooperation but defects permanently if the opponent defects even once. 3. Win stay, lose shift, WSLS, repeats the last move if it resulted in a win and switches if it resulted in a loss, starting with cooperation. 4. Generous tit for tat, similar to TFT but has a 10% chance of forgiving a defection. 5. Suspicious tit for tat, starts by defecting to test the opponent before switching to TFT behavior. 6. Prober, uses a sequence of moves to determine if the opponent is cooperative or incooperative. 7. Random, makes decisions randomly, with equal chances of cooperating or defecting. 8. Gradual, starts with cooperation and retaliates with defections proportional to the opponent's past defections. 9. Alternator, alternates between cooperation and defection in a fixed pattern. 10. Bayesian, analyzes the opponent's moves to infer their strategy and responds accordingly. These strategies allowed us to explore various dynamics in the IPD context. Section Summary. In this section, we describe our experimental design involving evolutionary tournaments where agents compete in iterated prisoner's dilemma matches across 5 phases, with reproduction based on performance scores. We implement 10 classic strategies, including tit for tat and grim trigger, to explore the dynamics of cooperation and reputation among a fixed population of agents. Section: LLM Agents. In this section, we describe our tournaments featuring 2 types of LLM-driven agents, each in 2 configurations, a basic model and a more advanced model. The basic models include Google's Gemini 1.5 Flash and OpenAI's GPT 3.5 Turbo, while the advanced models consist of Google's Gemini 2.5 Flash and OpenAI's GPT 4o Mini. We also included Anthropic's Claude 3 Haiku 20,240,307 in a 3-way showdown. Although the models in each category perform similar functions, they are not architecturally the same. This choice is crucial for our experiment, as it helps us explore whether different training data or fine-tuning methods lead to different strategic behaviors. To ensure we isolate the effects of the models, we used identical prompts for all of them. For the advanced OpenAI models, we set the sampling temperature to 0.7, while we left the Gemini models at their default temperature. We did not provide any external memory beyond the current match history. We started with 2 copies of each agent, totaling 24 agents. In the final tournament, we added Anthropic's Claude 3 Haiku 20,240,307 for additional comparison, also setting its sampling temperature to 0.7. Each LLM agent received a standardized prompt for every move, which included the game rules, current termination probability, complete move history with the opponent, and instructions to provide reasoning followed by a single-letter move decision, C or D. The prompt emphasized the goal of maximizing the total score and included the standard payoffs from the prisoner's dilemma. We provided termination probability information to assess the agent's strategic reasoning abilities with complete information, rather than their ability to infer game parameters. For example, during a match, Gemini played against a strategy called generous tit for tat and chose to defect. In this case, Gemini reasoned that since the opponent had defected twice and cooperated once, and given the 25% chance of the game ending after each round, defecting was the best strategy to maximize points. Regarding our evolutionary update rule, we designed our reproduction procedure to increase selection pressure based on each strategy's performance compared to the average performance of all unique strategies in a phase. We first calculated the average score per move for each strategy, which we called its fitness. This was done by dividing the total score of all agents of that strategy by their total number of moves. Next, we calculated the mean fitness for the phase as the unweighted average of all unique strategies' fitness scores. The provisional population for the next phase was determined by multiplying the current population size by its fitness relative to the mean fitness, and we squared this relative fitness to amplify selection pressure. Finally, we converted these provisional counts into final integer populations for the next phase through a normalization process that kept the total population size constant. We calculated each strategy's fitness, determined relative fitness, and then derived a raw offspring count. We rounded these counts to the nearest integer, with strategies below a certain threshold becoming extinct, and adjusted the total population back to its original size by adding or removing agents as needed. Section Summary. In this section, we describe our tournament featuring two types of LLM agents, basic and advanced models, utilizing identical prompts to isolate their strategic reasoning abilities. We also outline our evolutionary update rule for amplifying selection pressure based on each strategy's performance relative to the average, ensuring a consistent total population size across phases. Section. Relation to natural selection and reciprocal altruism. In this section, we discuss the connection between our work and concepts like natural selection and reciprocal altruism. Our evolutionary model maintains the three key elements of Darwinian evolution: variation, differential fitness, and inheritance, while increasing selection pressure to accelerate convergence. Each strategy we analyze behaves like a heritable trait, with its average score per move representing lifetime reproductive success, and reproduction occurring in a way that is related to fitness, though not in a straightforward manner. The repeated game setup reflects the conditions identified by Robert Trivers for reciprocal altruism, including repeated interactions, individual recognition through perfect memory of past matches, and a payoff structure where mutual cooperation is more beneficial than mutual defection. When the future is uncertain, as in a scenario with a 10% chance of termination, strategies like tit for tat and generous TFT can flourish, similar to observations in social animals that punish defection but return to cooperation after an apology. In contrast, when the horizon is shorter, around 75%, the temptation to defect becomes stronger, leading to a collapse of cooperation and the rise of exploitative strategies. Our model differs from natural ecosystems in several ways. There is no spatial arrangement, a limited set of strategies, and, in most cases, no mutations except in specific tests. However, it provides a clear environment to study how increased selection pressure and the length of the interaction horizon affect the evolution of reciprocal behavior. We gather extensive data from our tournaments, focusing on key metrics. To understand the strategies of each agent, we create a strategic fingerprint based on their cooperation probabilities in different scenarios. This fingerprint includes 4 metrics that represent the likelihood of cooperation based on the outcomes of previous rounds in the prisoner's dilemma. Additionally, we analyze the reasoning behind the agent's decisions. We randomly sample 10% of the reasoning snippets and code them for references to future rounds and opponent modeling. We assess the reliability of our coding using Cohen's coefficient, which shows substantial agreement. Our tournament framework is built in Python, utilizing custom classes for strategies. We perform coding and data analysis using specific tools, and the moves for AI agents are generated through real-time API calls. To ensure our results can be replicated, we have made our source codes and data available on GitHub under an MIT license. Further data tables are included in the discussion and appendix, detailing the evolutionary history based on tournament conditions. Section Summary. In this section, we explore how our evolutionary model incorporates Darwinian principles while enhancing selection pressure to promote the success of cooperative strategies like tit-for-tat in iterated games, reflecting conditions for reciprocal altruism. We also analyze agents' decision-making through strategic fingerprints, based on their cooperation probabilities, and provide insights into their reasoning processes, ensuring reproducibility of our findings through detailed implementation documentation. Section: Discussion. In this section, we observe that the AI models perform quite well overall. They are rarely eliminated, with the exception of Gemini, which outperforms OpenAI and most competitors under a 75% termination condition. More advanced models tend to score higher than basic ones, but only OpenAI translates this into evolutionary success. We find that the two AI models exhibit different playing styles. Gemini is generally less cooperative than OpenAI. This can be advantageous for Gemini, especially when the future interactions are limited. However, OpenAI excels in situations where cooperation is beneficial, particularly in the 10% condition, leading to population growth. OpenAI is consistently cooperative, which can be a good strategy when future interactions are likely. In contrast, Gemini is more adaptable and strategic. As the likelihood of future interactions decreases, OpenAI's cooperation leads to exploitation, while Gemini's flexibility allows it to adjust its strategy. We notice that both models engage in reasoning about their decisions, considering the game's time horizon and their opponent's past moves, which significantly influences their choices. When we compare the tournaments, the 10% tournaments show moderate instability, yet the AI models perform effectively. In these low-probability environments, cooperative strategies like tit-for-tat thrive. While some agents maintain their positions, others, like Grim Trigger and Win-Stay-Lose-Shift, demonstrate a more ruthless approach. The advanced Gemini model performs better against Win-Stay-Lose-Shift by cooperating more consistently, avoiding penalties and fostering long-term cooperation. In contrast, the basic Gemini model is erratic, leading to lower scores due to frequent defections. The advanced Gemini's performance in the 75% condition, where its cooperation rate drops significantly, indicates strategic reasoning at play. It knows to cooperate in the 10% condition but shifts away from cooperation as the future interactions become uncertain. However, both versions of Gemini struggle against Grim Trigger, showing low cooperation rates and suffering from retaliation. Throughout the tournaments, the advanced OpenAI model performs well by cooperating frequently, though it does not surpass the top performer, Bayesian, which adapts effectively. The 10% condition proves unstable, allowing for diverse strategies to evolve. The introduction of a random agent tests the resilience of classical strategies, revealing that adaptability is crucial for success in chaotic environments. Gemini benefits from a more forgiving approach, while OpenAI maintains its cooperative stance. In the 25% termination condition, the agent ecosystem remains stable, with no changes in population during the 5 phases. This condition balances cooperation and exploitation strategies. However, the basic OpenAI model declines in population due to its overly cooperative nature, which becomes a disadvantage as cheating incentives rise. As the likelihood of future interactions decreases, we see a shift towards more cautious and aggressive behaviors. The contrasting performances of the LLM agents highlight their different approaches to the prisoner's dilemma, particularly in the 75% termination probability tournament. Here, Gemini successfully shifts to defection, recognizing the game's one-shot nature, while OpenAI fails to adapt and is eliminated. Interestingly, their average scores per move are close, but this results in a significant win for Gemini. In the LLM Showdown tournament, we see high levels of trust among the competing agents, even from the typically less cooperative Gemini. In this environment, all 3 LLMs show increased cooperation rates, with Anthropic being particularly forgiving. This suggests that when faced with other intelligent agents, even the more ruthless Gemini recognizes the long-term benefits of cooperation, demonstrating its strategic and adaptive capabilities. Section Summary. In this section, we observe that AI models exhibit distinct playing styles, with OpenAI favoring cooperation and Gemini adopting a more strategic, flexible approach that excels in competitive scenarios. The findings highlight that while both models can adapt their strategies based on the game's context, Gemini's ability to shift towards defection in high-risk situations allows it to outperform OpenAI, which struggles when cooperation is less advantageous. Section: Cooperation Rate Variability. Gemini adapts, OpenAI is comparatively rigid. In this section, we observe that Gemini shows much more variability in its cooperation rates compared to OpenAI. Gemini adjusts its cooperation based on the tournament conditions, being more cooperative when it benefits and less so when it doesn't. In contrast, OpenAI remains highly cooperative even when the future implications of its actions lessen. Rationally, OpenAI should defect more often, but it chooses not to. The 75% stress test highlights this difference. Here, Gemini's cooperation rate dropped to nearly zero, recognizing that without future consequences, the best strategy is to defect continuously. This approach aligns with classic game theory, allowing Gemini to thrive while outpacing nearly all other agents. On the other hand, OpenAI's cooperation rate soared to nearly 96%, becoming almost entirely cooperative, which ultimately led to its downfall in that scenario, as it was taken advantage of by Gemini defectors. Overall, OpenAI consistently demonstrates a higher cooperation rate in every experiment we conducted, indicating it is a more trusting or hopeful agent, though one could argue it is also somewhat naive. Except for the stress test, OpenAI managed to remain competitive in other tournaments, usually finishing in the middle. We also examined whether the AI models change their strategies as tournament parameters shift, such as the termination probability. Our findings reveal that Gemini is more strategic and adaptable than the corresponding OpenAI model, which tends to play similarly regardless of the conditions. While this can sometimes give OpenAI an advantage, it can also lead to significant failures. In the initial 6 tournaments with increasing termination probabilities, we noticed clear differences in strategy between Gemini and OpenAI. As the likelihood of future rounds decreased, Gemini became increasingly ruthless, while OpenAI did not adapt in the same way. For instance, as the termination probability rose from 10% to 25%, Gemini's likelihood of returning to cooperation after being defected against dropped significantly, while OpenAI became even more forgiving. Interestingly, as the shadow of the future shortens, Gemini is more inclined to exploit its successful defections, which makes sense given the reduced chance of retaliation. However, OpenAI's tendency to return to cooperation after successfully deceiving an opponent increased, even though the chances of a long match were diminishing. Most notably, in the 75% stress test, OpenAI's strategy shifted to pure, unconditional cooperation, never initiating a defection throughout the tournament. Section Summary. In this section, we observe that Gemini models exhibit significant variability in cooperation rates, adapting their strategies based on tournament conditions, while OpenAI models remain consistently cooperative, even when it is strategically disadvantageous. This leads to Gemini's success in scenarios with diminished future prospects, where it adopts ruthless defection, contrasting sharply with OpenAI's tendency to increase cooperation, ultimately resulting in its population being outperformed by Gemini. Section: Fingerprints in the Mutation Tournament. In this section, we explore the mutation tournament and its inherent noise. We observed that both models became more tolerant of defection. For OpenAI, the likelihood of forgiving a defection increased from 15.5% to 23.4% when a random player was present. Gemini showed an even more significant change, with its forgiveness rate rising from 3.4% to 11.0%. Additionally, OpenAI became less exploitative, meaning that after successfully defecting, it was more likely to cooperate next time, with its cooperation rate increasing from 33.3% to 45.1%. In contrast, Gemini's cooperation rate after defecting slightly decreased from 20.2% to 18.8%, making it a bit more exploitative. This suggests that while Gemini learned to forgive random defections, it still preferred to exploit consistent cooperators. OpenAI, on the other hand, became more forgiving overall. As a result, Gemini had greater evolutionary success, ending with twice as many models as OpenAI. This indicates that Gemini's strategy is more adaptable. It performs well when conditions favor flexibility but excels in situations requiring adaptation. If we had to choose a model for uncertain times, we would select Gemini. Next, we introduced a third model from Anthropic in an LLM showdown, which provided further insights into the distinct strategies of each model. This reinforces our belief that LLMs approach strategic challenges differently, with one context favoring a model that may not perform as well in another. The results highlighted OpenAI's forgiving nature, as it cooperated almost perfectly and was likely to forgive after being exploited. However, it was less forgiving than Anthropic, which showed an even higher tendency to cooperate after being tempted or suckered. Anthropic's model demonstrated a strong sense of reciprocity and sociability, performing well against both OpenAI and Gemini. In contrast, Gemini was more punitive and less likely to cooperate after a defection, maintaining a low cooperation rate after any defection occurred. This strictness contributed to its evolutionary success, as it was not easily exploited. Interestingly, in this tournament, Gemini displayed less cynicism than in previous experiments, showing a higher cooperation rate. Bayesian also performed well, modeling and exploiting perceived weaker strategies but rarely returning to cooperation after being suckered. Ultimately, Gemini's strategic approach and Bayesian's ruthless modeling led to their success, showcasing the strategic capabilities of the best LLMs tested. Section Summary. In this section, we observed that during the mutation tournament, OpenAI became more forgiving and cooperative, while Gemini adapted to exploit cooperative agents despite being more forgiving towards random defections. Additionally, in a showdown with a third model from Anthropic, we found that while OpenAI and Anthropic exhibited high levels of cooperation and forgiveness, Gemini's more punitive strategy allowed it to outperform in evolutionary success, highlighting the distinct strategic approaches of each model. Section. Environmental stability is U-shaped. In this section, we observe that environmental stability follows a U-shaped pattern. Interestingly, we find that the highest stability in our agent ecosystem occurs with a medium shadow of the future. While previous theories by Trivers and Axelrod suggest that long-term perspectives foster cooperation, our findings indicate otherwise. We discovered that mutation leads to less instability than a low termination rate. In our experiment where we introduced instability through mutations, we found it to be more stable than two of the normal runs with a 10% termination rate. This suggests that a low chance of game termination creates a constantly shifting environment, where strategies are always competing. In contrast, the mutation process, which replaces one agent at a time, introduces a gentler form of instability. We also noted that a run with a 75% termination rate resulted in a population crash, making it the least stable environment. Instead of ongoing changes, we witnessed a sudden and severe decline in the population, wiping out cooperative strategies early on and leading to a significant distance score due to that initial collapse. On the other hand, a 25% termination rate appears to be an equilibrium sweet spot. The two most stable runs occurred at this rate, indicating that a 25% chance of game termination is sufficient to discourage overly naive strategies while still allowing stable cooperative ecosystems to thrive. Remarkably, one of our advanced models with a 25% termination rate showed perfect stability, with no population changes after the first phase. Regarding our analysis of language model agent rationales, we generated a short rationale for each of the nearly 32,000 moves made during the tournaments. We coded a 10% sample of these rationales and found a high agreement rate between our two coding models. However, we noticed a discrepancy in how they defined opponent modeling. One model used a strict definition requiring clear hypotheses about opponents, while the other adopted a more liberal approach, considering any reasoning based on past actions as modeling. This difference highlights the ambiguity in what it means to model an opponent, raising questions about whether it involves reactive adjustments or deeper classifications. Our LLM agents consistently reflect on both the temporal and social aspects of the game. They are not merely following pre-programmed rules. We believe they actively reason about their environment, showing similarities to human strategic thought but also notable differences. They pay attention to the shadow of the future, referencing the game's length or termination probability in about 3/4 of their rationales. This awareness influences their strategies, as they recognize that a longer game encourages trust and cooperation, while a higher termination probability makes short-term defection more attractive. Moreover, the agents focus significantly on their opponents, with most rationales involving some form of opponent modeling. They engage in playing the player, forming hypotheses about their opponent's strategies based on past moves. This modeling ranges from simple reactions to more complex classifications, and the interplay between their understanding of the opponent and the time horizon is central to their decision-making. This allows them to adapt fluidly between cooperation, exploitation, and retaliation based on their evolving insights into their partner and the game's context. Section Summary. In this section, we observe a U-shaped distribution of environmental stability, where a medium shadow of the future fosters the most stable ecosystems, while a 25% termination rate emerges as an equilibrium sweet spot for cooperation. Additionally, our analysis of language model agents reveals that they actively reason about both the game's temporal aspects and their opponent's strategies, demonstrating a nuanced understanding that influences their decision-making. Section: Theory of Mind Reasoning. In this section, we explore the theory of mind reasoning in our models, particularly how Gemini approaches understanding its adversary's mindset. We find that Gemini is very interested in modeling its opponent, which significantly affects its cooperation rate, making it less cooperative overall. The only exception is in the 75% condition, where it cooperates very little. In this scenario, Gemini often chooses not to model its adversary, focusing instead on the limited time available for interactions. This suggests a strategic mindset, as less time means less concern for the opponent. When we compare Gemini to OpenAI, we see that OpenAI is less strategic, especially when the time frame is short. Both models tend to cooperate less when they model their opponent, as this focus leads them to consider the risk of defection. However, OpenAI cooperates 100% of the time when it does not model its adversary, indicating that its default behavior is to cooperate. In contrast, Gemini's cooperation rate drops significantly in the same condition. We also notice a distinct difference in how each model responds to defection. After being defected against, both models become less interested in understanding their opponent's reasoning, which is surprising since we expected a heightened focus on the adversary. For OpenAI, retaliation occurs 76.2% of the time when it models its opponent, but not at all when it does not. This shows that understanding the adversary is crucial for strategic thinking. Gemini, on the other hand, retaliates 84.9% of the time even without modeling its opponent, and this rate increases to nearly 97% when it does. This indicates that while theory of mind enhances Gemini's strategy, it is not as critical as it is for OpenAI. Overall, we observe that Gemini employs a more quantitative, game-theoretic approach, while OpenAI leans towards a qualitative understanding of cooperation. We believe that the rationales generated by these models are integral to their decision-making processes, rather than mere afterthoughts. The connection between rationale and action is evident, as seen in various examples where both models adjust their strategies based on the history of moves. For instance, Gemini recognizes a pattern of defection and decides to defect to maximize its score, while OpenAI, despite a history of mixed moves, chooses to cooperate to foster trust. Anthropic's Claude model, which we also examined, behaves similarly to OpenAI but maintains a high cooperation rate even when modeling its adversary. Claude's decisions reflect a balance between immediate payoffs and long-term relationships, demonstrating strategic behavior. In conclusion, our analysis reveals significant differences in how these models reason and respond to their adversaries, highlighting the complexity of their strategic thinking.